In this video I'm going to ask how much force can a human exert. We'll then compare it to how much force in principle could be exerted and see whether the humans are up against the fundamental limit. So let's take a human exerting some force. Now here's me raising my body weight on one leg, which is a moderately strenuous activity for most people. So what I can do is I can straighten my leg, there's my body mass, and push myself up. So the upward force that my leg is exerting is as great as, or greater, slightly greater than, the downward mg. So that's telling me that my leg can apply a force roughly equal to my mass, which is 70 kilos, times g, which is 10. So about 700 newtons is the force my leg can exert. Now we're going to have to factor in the fact that some muscles are bigger than others. My leg thigh muscle is the biggest muscle in the body, and so it's going to exert a lot more force than, say, the muscles in my little finger. So we've got to factor that in somehow. And the way we normally do that is to divide the force by the cross-sectional area. So the idea is that by this metric, force divided by cross-sectional area, different muscles will come out about the same, and indeed they do tend to. So what's the cross-sectional area? If I slice my thigh open here, you can see from the ruler it's about 10 centimeters by 10 centimeters. So the area is about 0.1 times 0.1 equals 10 to the minus 2 square meters. And we can define what's called the stress, something any structural engineers amongst you will get very used to in this term, which is defined as the force divided by the area, and that's going to be about 700 over 10 to the minus 2, which will come out as about 7 by 10 to the 4, so ballpark 10 to the 5 newtons per meter squared. So that's a rough estimate of the strength of the human muscle, at least my human muscle. But I'm not exactly an elite athlete. Let's look at someone who is an elite athlete, Usain Bolt. Can we work out how much force he's exerting? Well, one way to do it is look at how fast he accelerates off the block. We know that F equals ma. So if we can work out his acceleration, how fast his velocity is increasing, we'll be able to work out at least a component of the force in this direction that's pushing him along. Well, it just so happens there is data for this. So what we have here is his velocity against the time during a 100-meter sprint. And what you can see is the velocity starts at 0, as you'd expect at the blocks, rises very quickly, and then flattens out at about 12 meters per second. So what is the acceleration here? Acceleration is the rate of change of velocity, so it's the gradient of this curve. We can work out the average acceleration over, say, the first 2.5 seconds. So in about 2.5 seconds, it's gone up to about 10 meters per second. Therefore, the average acceleration, a little bar over the top to show it's an average, is going to be about 10 meters per second over 2.5 seconds, which is going to come out as about 4 meters per second squared. Is that his peak acceleration? Well, not really. What you can see is the slope of this curve is constantly changing. So where it's steepest is going to be down here, and that's actually going to be rather more acceleration. So here what I've done is I've actually drawn a tangent line. I've attempted to get a line that's tangent to the data, that has the same slope as the data right down here at time equals 0. And in this case, it gets up to 10 meters per second in only 1 second, going through that point over there. Therefore, the acceleration is roughly 10 over 1, which is, of course, 10 meters per second squared. So that's quite a bit more. So it looks like his acceleration right off the moment when he's pushing off is about 10 meters per second. It's dropped to about 2.5 meters per second squared. 2.5 seconds in. It's dropped to about 4 meters per second squared 2.5 seconds in, and then out here it's pretty flat, so its acceleration drops to 0. Now, that's not the only force going on here. His centre of mass when he's crouched at the blocks might be about there, and its centre of mass has moved up to about here. Therefore, there must be a net acceleration in that direction. We know there's a downward force of gravity, and the force, his leg is pushing down on this, and it's therefore giving a pushing back. And that force must be something like this direction. So if we add up the gravitational force down and the force from the push, it accelerates his body in this direction. So there's going to be a force from his foot in this direction, and when you add the gravity in, it'll come to something like that as a vector sum. We could divide the force into two components, a horizontal and a vertical force. And when you add in the weight, it must point along his body pretty much, because that's where he's been accelerating. Now you can see from the angle here, it's not too far off a 45-degree angle. That means these two components are going to be roughly the same, and by Pythagoras you've got a triangle. We've got this side, and that's this side there, and the hypotenuse is just the root of the length 1 squared plus 2 squared, which means that the total force is going to be about root 2 more than either the horizontal or the vertical force. What is the force? Well, we said he accelerated at about 10 meters per second squared in the horizontal direction. So the horizontal force equals mass times the horizontal acceleration. His mass is about 100 kilos, so it's about 100 times 10, so it's about 1,000 newtons. And vertically, it has to be roughly the same, so the sum of the two is going to be about root 2 times that, which is going to be about 1,400 newtons. So actually, the force that Usain Bolt exerts is not that different from the force I exert. I'm putting out 700 newtons, is 1,400, that's twice, but of course he is an elite athlete, has much thicker leg muscles than I do. So in fact, the force per unit area is probably not that different. In fact, it seems to be generically true that from most muscles in most animals, you've got a force, a stress, of roughly 10 to the 5 newtons per meter squared. Sometimes it might be 2 times that or a half times that or something like that, but roughly speaking, that seems to be the stress in all animal muscles. So the next question is why? Is there any fundamental reason why a muscle of a given cross-sectional area is limited to this type of stress?